Hello everybody, thank you for joining us today. My name is Minam and today we're going to be looking at the life cycle of a star. Now this is actually my favourite topic in physics, so some of our learning objectives include to understand the life cycle of a star around the size of our sun, so a sort of average star, and to understand the life cycle of a star much bigger than our sun. Now let's get started with the life cycle of a star. Now every star, no matter how big or how small, all comes from the same thing called a stellar nebula. Now this is really just a fancy way of saying a place with dense gas clouds. Okay, so that's all it is. We're really talking about hydrogen gas here because that's the most abundant element in the entire universe. So we have here stellar nebulas, which are just areas where the concentration of hydrogen is very high, right? We have very big and large clumps of hydrogen together. Okay, now that we have huge clumps of hydrogen together, there are also large, well, actually, not really large. There are gravitational forces between clouds of gas. Okay, so say I had one cloud of gas over here and I had another cloud of gas over here. These two, due to gravity, would be attracted to each other. Okay, so now say we have a sort of average average size of a gas cloud, right? So these clumps of gas start to be attracted together, and over millions of years the force of gravity sort of merges them together to form a very a sort of simple average star. But really there's a sort of a space here for something called a protostar. Okay, so that's really just the first stages of a star. Okay, so as a clump of gas comes together, they sort of stick together and they form a protostar. Now, after a protostar, they reach onto another stage called an average star here, but this is really an average main sequence star. Okay, so this is sort of the main bulk of the star's lifetime, right? So the star really exists in this form for 90% of its life. So 90% of a star's life is in its main sequence form. So here I have average main sequence because we're talking about average size stars such as our sun. Okay, so when they're in an average size star, two forces are acting upon a star. So let's say I have my star right there. Inside the star, if you remember from an earlier video, there's something called nuclear fusion going on, okay? Because there's so much mass here, right? So much hydrogen that all those hydrogen particles are being attracted to each other by gravitational force. Okay, so gravitational, and I'm going to use the word now, pressure here. Okay, so all of these stars are being, this star is being squashed together really tightly to form by just the sheer gravity of the actual star itself. Now, when you force together particles really closely, something called nuclear fusion happens. Now, nuclear fusion is when you join together two light nuclei to form one big nuclei, right? And the result of this is energy being released. So this gravitational inwards pressure is also balanced by an outwards nuclear pressure. Okay, so that's nuclear pressure due to fusion. Okay, so the fusion happening in the star releases energy outwards, and then the gravity of the actual size of the star pushes it inwards, and these two forces for majority of its life are balanced, hence why the main sequence star is the majority of where its life stands. Okay, so when these two forces are balanced, the star exists in a main sequence. Now, after a while, the hydrogen that the star is fusing starts to run out. So hydrogen starts to run out. Okay, so now the hydrogen is running out, the star has to fuse helium. Helium needs to be used up. Okay, so we really talk about these elements as sort of being fuel for the star. Now that the helium is being used up, a little less energy is being released, so the nuclear pressure outwards sort of drops. But as a side effect of this, the outer ring of the of the star starts to expand. Okay, so so let's write here, outer ring expands. Now, when things expand, surface area increases. That means that they can lose energy faster. So when they lose energy faster, they start to cool down. down. Hence why it goes from a sort of whitish yellow to a red, right? Because white is really like the hottest ish color, and then you get cooler and cooler, and then we start to get into a form called the red giant. Okay, now after a while, the red giant starts to lose its helium as well, so it has to fuse other elements which give it even less energy, and that continues and continues and continues till the outer ring of the actual star itself simply doesn't have any fuel left anymore. So the outer ring is shedded, so sort of like how a snake sheds its old skin, right? So star runs out of fuel and sheds outer layers. Okay, so when it sheds outer layers, it leaves a very dense, a relatively small now core called a white dwarf. Okay, so let's write that down here. Dense, small core called white dwarf. Okay, so this is white right now because it's no longer fusing any sort of elements. Okay, it's no longer fusing any more elements, so energy really isn't being released anymore. So when we don't really release energy, we can only lose it, so the star starts to cool down. After a white dwarf, we get another stage called a black dwarf, which I'm just going to write here. I'm running out of space. We start to get something called a black dwarf. Okay, so I've sort of run out of space. I hope you can see that, right? So a black dwarf is when the star has completely cooled down to sort of background temperature. So background temperature in space is pretty much 0 Kelvin, right? So that's negative 273 degrees Celsius, right? So that's a black dwarf when the star has lost all of its energy. But that really only happens in billions of years. And I think, as far as we know, black dwarfs are only a theoretical concept, and we haven't actually observed any of them. Mainly because it's really hard to observe something that's not giving off any energy. Okay, so that's something that we're going to have to look at next when we look at the life cycle of a star much bigger than our sun. Okay, so that's this this one over here, right? So we're going down. So if the initial clumps of gas in the stellar nebula are much bigger than the average size of our star, they come together to form a massive star in its so first they form again a protostar, right, but just a much bigger one, and then they form a massive main sequence star. Okay, now what you need to understand is that the real difference between an average star and a massive star is that the massive star runs through its fuel much faster. Now that sort of makes sense, right? Because think of it sort of like a sports car versus a family car, right? Sports car goes faster, so we can sort of think about it going faster as sort of like its size, right? So it goes faster, so it runs out of petrol faster. Okay, it runs out of petrol faster. That's sort of akin to the way a massive star or goes faster, right, grows bigger. It runs through its fusion much faster, and so it loses its initial hydrogen fuel much faster, right? So when it loses this initial hydrogen fuel, the outer ring again starts to cool as we start to fuse helium, and then again, because we have so much of the star, right, so much initial mass, we don't just get a red giant, we get a red supergiant, right? So the super really tells you that the initial star was much bigger. Okay, so now this again, it stays in this form for a much shorter time as well, because it's bigger, it's running through everything much faster, and so it stays in each stage for a much smaller amount of time. Okay, eventually when the time comes that we've fused all the elements that we can fuse and we reach iron, so iron is the most stable element in the periodic table, so that means that you can't fuse iron anymore. Once you get iron being fused, the inner core is so dense that suddenly the huge gravitational force is acting upon it. Because remember, a star is only stable as long as its gravitational pressure inwards is matched by the nuclear pressure outwards. Suddenly, we've run out of elements to fuse. We can't produce any more nuclear pressure, so therefore, that the gravitational pressure is suddenly overpowers the nuclear pressure. It compresses, it collapses the star into itself. the outer layers bounce off the inner layers, and you get a huge explosion called a supernova. So I'm sure you can tell by the image, but this is called, that is an explosion, but this isn't, I'm going to write it here. This is an explosion, and it's called a supernova. Now, for a few days, this is the brightest thing in the universe, okay? So think of the billions of billions of billions of stars. For a few days, this one explosion can outshine every single one of them, okay? So it's a really big and really, really uncommon event for a supernova to happen, and it's not one that we understand at all, actually. So even when you get to A level, you really understand that we don't understand them at all. Okay, so after a supernova, we can go one of two routes. We can either go the neutron star route. So this is when the star is quite massive, right? So this is a neutron star, which is in the name, it's only made up of neutrons. Because remember, even though we have all of this fuel in the star, right, it just boils down to three things, right? Protons, neutrons, electrons. But in a neutron star, the electrons and the protons have been shoved together, and then they turn into neutrons. So this is like a really dense, really tiny soup of neutrons, right? Okay, and this is also sometimes called a pulsar, but that's not really something you need to know at GCSE. That's only if you come across it in your revision. Okay, it's called a pulsar because it sends out these pulses of energy from its top and bottom. But if the initial star in the stellar nebula was huge, now I'm talking ridiculously massive, so like something like 1 billion suns mass, instead of a neutron star, we get something called a black hole. Now, a black hole is literally something that breaks physics. So I have here a theoretical image of a black hole here, and then I have the real image that we've seen, and this only came out last year, so you're really looking at cutting edge physics here, and you can see that our theoretical sort of matched the real image that we found. Now, a black hole is a sort of infinitely small point that has infinite density. Now, don't worry if you don't really understand what that means. PhD physicists don't even understand what it means. But a black hole is really a place where the gravity is so strong that nothing can escape it. So not even light, which is one reason that we can't actually see the black hole itself. Like if I was to put a dot here, right? Oops. That dot is still bigger than a black hole by about like a few billion times, right? So it's something that is really, really difficult to imagine, but you just need to understand that it's a place with sort of infinitely high density and so extremely strong gravity, and nothing can escape from gravity. Nothing can escape from its gravity. We can see here that this shape in the actual diagram itself right here kind of looks like our Milky Way. Well, that's on purpose because right at the center of our Milky Way is a black hole, right? So that's why we sort of get the swirling shape, because right at the center, the black hole's gravity is so strong that it's causing all the planets to spiral into it. So you can think every second in the universe, right, one planet, well, actually even more than one, probably thousands, right, get sucked up by a black hole, and they get turned into, well, pure energy, right? We don't really know what happens from there. Okay, so I know that was a huge amount of stuff right there for you to learn, but if you can understand the life cycle of a star much bigger than our sun and the life cycle of a star much smaller than our sun, the average size of our sun, you're well on your way to understanding your physics GCSE.